Hi, it's T. In this video, I'm going to go from start to finish a machine, how to run a machine learning model. I'm going to be going through what to do and why it's done. And essentially, this is going to be like a template for you going forward. So using this, you'll be able to, work on different machine learning models. And just to show that this is going to be different from other videos, I'm starting at what we're going to do. I'm going to explain it because like a lot of the training out there, like when I was learning how to work with these different models, they don't really explain it properly. So what we're doing with the machine learning model is we are trying to predict, we're trying to predict these three flowers. So we have versicolor, virginica, and setosa. These are three different flowers. And if I bring a flower to my model, I show my model a flower with a certain petal length, a certain petal width, and a certain sepal length and sepal width, it will accurately predict which flower it is based on this data. So that's what I'm trying to do with my machine learning model. And I will be training my machine learning model with um with a data set with that contains this information. So the machine learning model will be trained, it will be taught that when we have a flower with this petal length, with petal width and sepal length and sepal width combination, we get this flower. So that's how we train our model. But again, you want your model to be, well, not again, firstly, but again for me, because I have to keep, you as a data analyst working with learning models, you need to make sure your machine is generalizing and not memorizing, you know. So I'm going to go into more detail. So here we go. And the data set we'll be working with is the IRIS data set. It's used a lot of data scientists and data analysts or anybody working trying to learn data manipulation. They're usually going to be familiar with, or they're going to come across this data set because it's a easy data set, well understood, clean data set, which is important so that you can use it for the purpose of teaching and you can get right into your machine learning model, because in some instances you're going to have messy data, which is real world data, with there's going to be gaps, there's going to be NAs, there's going to be sections with NAs, and their things are not going to be in the right formats, and you're going to have to transform it to another format, and like that takes you away. Like that's very important, to learn how to do that, but that's a separate thing. That takes you away from what we're trying to do now. We're trying to just learn how to run a machine learning model. Machine learning model we'll be looking at today is KNN. We're gonna have to do some analysis. Anyways, you always have to analyze your data. That's standard, and you're gonna have to do some pre-processing before you use a machine learning model. So we load from, it's a library. It's inherent to Python. So from the sklearn library, we import iris. So import load iris. That's sklearn data sets, and we import load iris data, and then we're gonna call the data. This is what our data is gonna be called. It's gonna be, so we're assigning load iris dot data, and we're calling it data instead of having to type this out the entire time. So that's basically all that's happened there. Um, and this is what the data looks like. So again, it's not in a nice, clean data frame format. And yeah, it's nice to see this as well, because you can get data like this as well, real world data. But we understand this data set, that's why it's generally used. But what is happening here is we've got four columns: two, three, four, with different data. So you load the data, which is those four columns are these variables: the petal length, petal width. These are four, and sepal width. That's these four. You have to, the labels are separate. So then you go, this is the data shape, like I said. So we have 150 rows with four columns, the sepal length and etc. And then you need to load the target or the labels separately. So from the library dot target, and we're calling it labels. We could call it name, or we could call it species. We're calling it labels in this case, which is basically saying what. So we have we say this is one row. We have these different variables, sepal length, sepal width. I don't want to keep saying every single time. And then we'll have the label, which is what is it? So the label is a versicolor, virginica, and so on, etc., etc. In this case, it's in 0, 1, and 2. A lot of machine learning models will require you to have the the label in this format, but in this case, we're going to change this shortly. But here we're going to next, and I have loads of notes on this. Please don't let the notes deter you. The notes are important. You need to read them. If you're ever feeling stuck, read the notes and just check what's going on. I take a lot of notes and then just check what's happening. So in this case, we're importing another library, the NumPy library, and then we're going to use this to, because now we want to connect this data to this data to make our data set. You need to match what you get with the labels of the data set. And then we're going to reshape our labels data set that we loaded earlier. Remember, loaded labels from the library. And we yeah. So we're gonna reshape this. And why are we reshaping it? That's probably a question you have. Or we're reshaping it because it's in one dimension. We need it in two dimensions. It's in a one-dimensional array. We need it in two dimensions, like this data, this array, so that it can concatenate. The only way we can join them together if they're in both in they both have the same dimensions. They won't connect otherwise. So that's the whole purpose of this code. Reshape, adding an additional dimension to that array. And then now that that's done, in this section, I'm just naming it data, the connection. So this is the data with the labels, and we're gonna call it data. And now what will happen is we're gonna have an extra column. This column contains all the labels, and this is it right here. Now we need to get into a clean data frame first, but I'm just so you can see what's been done. So here we've imported we import pandas as PD, so it's just easier to work with rather than typing pandas the entire time. And here we know the organization of the columns. We understand the data set well. So in case you're asking, how do we know this sepal is the first column? We inherently understand the data set already, so we know sepal length is the first, sepal width is the second, that we're adding to something that is like that, but with the species section added as well. So just keep going back and forth just so there's full understanding. I want this to be as detailed as possible because I find if you miss a little bit of the details, if you miss some of the details, you get lost and then you just veer away, and you just keep digging yourself into a deeper hole of misunderstanding. So I feel like you need to get all of the little details to continue to build on your understanding. So yeah, so these are the names that we've initialized into this names. And then we have the data set. This is what we're going to call. So pd.dataframe, which is the data, and then we want the columns, and then we equals names for all these, and then we're going to make it a data frame. That's the pd.dataframe. I'm going to make our data set with, which is this 150 rows, five columns. Now we're going to name it so it's nice and neat, and we're going to make it a data frame, and then we're going to look at the first five. So data set, we've called it data set. I'm going to go dataset.head 5. So we're going to look at the first 5 rows of data set, just see what it looks like. And this is what it looks like. This is our final product ready to work with. But we still have it like this, you know, which is, that's not as obvious. You want it obvious to someone looking at it, like, what is the species? Species 0. Now, species 0, as we understand from this, species 0 corresponds to Setosa, and then species 1 corresponds to Versica, and species 2 corresponds to Virginica. And basically all we're doing here is we're getting our data set and we're looking at the species column and we're using the replace function to replace 0 with Setosa, 1 with versicolor, 2 with virginica. So then when we look at the first 5 rows of the data set again, this is what we see. Now this data set is very, what's the word for it? I'm gonna say it's continuous. So the first 50 are Setosa, the next 50 are Versica, and the final 50 rows are Virginica. So if I was to look at the tail of this data set now, so if I said I didn't really, I probably should have added in because I just wanted quicker. I think it's quicker if I don't have to type in the code. So the that should be the final. The tail should be the 5 rows from the bottom of the data set. And here we see Virginica. So that's essentially it. The final 50, or if I put 50, you can see all 50, but I don't think it's necessary. I hope you get the gist from that. So I will pause it there. Right, so we just completed loading the data, and now we're going to do some analysis of the data. Let's have a look at what the data looks like. So to have a look at the data, to visualize data, we're going to do matplotlib, and we're going to use the library matplotlib, and we're going to load it as PLT. It's just easier to work with. Now we're going to make a scatter plot. I remember what I said. The first 50 rows are Setosa, and then essentially we're looking at data 50 to 100 is versicolor, and the final 50 is iris virginica. And that's all we're doing here. And we're looking at 0. So we're looking at column 0 and column 1. If you remember, so column 0 is sepal length. That's how Python works. It goes 0, 1, 2, 3, 4. So technically, if we're looking at this, so I might do this interchangeable, but just keep it in your mind because that one has got me before. That's got me before. I was getting confused. I forget what the situation was, but I got a bit confused about that. So just remember, we have here, we're looking at 5 columns. In everyday life, you're looking at 5 columns, but in Python, we have 4 columns. We still have five. You still have five, but it goes 0. It starts counting from 0, essentially. 0, 1, 2, 3, 4, right? So just keep that in mind. I'll try to stick as best I can to just normal speech, which is 1, 2, 3, 4, 5. But I'll make sure to make that clear as possible. But if you ever find yourself getting confused, just remember that it's 0. Okay, enough of that. So here, essentially, this is where we have to go to Python speech, which is we're looking at column 0, which is sepal length, and we're looking at column 1, which is sepal width, and we're doing a scatter plot against that for Setosa, versicolor, and virginica. So here we have sepal width and sepal length. So column 0, column 1 for all the different species, and we can see that there seems, what I noticed from looking at this is that there is a strong correlation when it comes to Setosa. There's a strong correlation between sepal length and sepal width. So essentially, I'm saying that once the sepal length is large in Setosa, it tends to be large in the sepal width tends to be greater in in Setosa. There's a correlation, a positive correlation. This goes up, that goes up. It's the correlation is not as strong when it comes to the other two species, which is interesting. We might be able to classify the species based on this. And just to go more into this, because I don't want to fly through this too quickly, the rest of it isn't that important. It's just labeling, and I'm pretty sure you should be able to decipher this. Font size, you can play around with that and just see which one suits you best, which one you prefer. And so it's fairly straightforward, this PLT. So this is This is the data, and then we're taking the first 50, then the next 50, then the last 50, so that we have the right species, because it goes the first 50 Setosa, second 50, and so on and so forth. We're doing that for here. We're doing it for the sepal width, and then here we have to do the same for the sepal length in order to make the scatter plot. So yep, finish there, and then we're gonna do it. We're gonna take the number two, which we're looking at the petal now. So petal length and petal width. And for all species, it's essentially the same thing as above, except we're changing the columns we're looking at for each of the species. And now we can see that there's a way stronger correlation. So there's a way stronger correlation with the petal width and petal length, and we're going to see this in a heat map. So a heat map is a nice way of viewing correlation. The lighter the color, the greater the correlation. The darker, the not so good the correlation. So based on this and what we've seen above, we can determine that if I see petal width and petal length, we're gonna have a high correlation between these columns. And so let's go to petal. So petal length and petal width, 0.96. Best correlation is 1. So very close to 100% correlation, which is 1. And then then you can look at, if you look at sepal width and sepal length, for example, sepal width, sepal length, not as good. Sepal width and sepal length, very low. Sepal width, sepal length. This is taking into account all the species. Now we noticed that there wasn't really correlation between Iris versicolor and virginica, but although we did have great correlation in Setosa, but overall not great correlation. Even in just normal predictions, more much more simpler prediction, you can base off the length. For example, we can nearly say in this case, this is the good thing about analysis. We haven't even done the machine learn. We haven't used the machine learning model, but from looking at this data here, we can say that if we see a species that has a petal length in the range between 3 and a petal width in the range of 1, like within this square. I can't put a square in, but within this square, we can say it's likely that that species is a Setosa without using machine learning model for help. So that's a nice thing to keep in mind. Done the heat map, and now we get to pre-processing, which is the next step. Okay, now we're in the pre-processing of the data. Because we have good understanding of this data, we won't need to do any pre-processing of the iris data, but in real life data, you will have to do some level of pre-processing of data. An example of this would be normalizing the data, which is essentially you're bringing the data into scale. So, for example, let's say the x values had high numbers in the 50s and 60s, and then the y values, the range of numbers were in between 1 and 10. So that means x value will have an overpowering effect when it comes to machine model to the y value, and we don't want that. So you bring it into scale using different methods. Normalizing is a method, but it's based on your data. So if we had done some early data analysis in this project, we would see the shape of the data. The shape of the data will determine what type of scaling you do. So it could be normalizing, it could be a min-max scale to bring it into a range for the model. And then after you unscale it to get the answer in the format you want. I'm not going to go into that too much because that can be for a different video. This video is based on the machine learning model. So in this case, we don't have to scale the data because looking at the dataset.describe function here, we can see that all the data is within the min and max of data are within the 10, so no scaling required. Now, one of the most important parts about and when it comes to running a machine learning model is splitting of the data. In this case, you're keeping some data. No, you're training the model on some data. And then after you train the model on a certain amount of data, then you're going to test the model to see how well it will work on the real world with a portion of the data. So in this case, we're going to be doing 80-20 split. So 20% is the test size. And I'll just go and explain this again because this can get lost if you're seeing it for the first time. It's a very important part. So when you're training the model, you're telling the model, this means you're telling the model what to look out for. You need to give the model something. So in this case, we're telling the model when you see a petal length and petal width, sepal length and sepal width of this combination is versicolor. Different combinations, virginica. Different combinations, setosa. So when we bring a flower that we don't know, now the model is only trained on these trees, so it has to be one of these trees. So if we bring a flower that we don't know into this model, it will determine which one it is for us. It will classify it based on the training. So how well you train the model is how well it will work when it sees a combination of petal and petal width that it has not seen before. That's the purpose of this whole project, is to be able to classify the flower based on the combination based on the variables outlined, the petal length, petal width. Okay, getting too far ahead of myself. So what we do is we import in the train test split from the sklearn library. That's all we did there. Then we're getting the data set and we're taking tree. And the first tree columns, if you're eagle-eyed, you'll notice that we're taking tree columns. There are four columns, which are the four variables I discussed. Why we're not taking petal width is because if you remember, it had a strong correlation with petal length. So the information to the machine learning model is redundant. So we're leaving out petal width because it's just redundant information. Because they're highly correlated, we know they're giving the machine essentially the same amount of information. And if you can find ways to simplify your machine model, you should always do that. So we've removed that column from this project. And that's why we're taking first tree. And 4 means index 4. I remember what that means. So that's 0, 1, 2, 3, 4. That makes it the fifth column, which is the species column that contains the information we want. So we're going to separate the labels. The labels are being separated from the data. And this is outlined here. So this is the training set, which is 120 tree 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 variables, and then these are the 120 labels for the train set, and this is the test set. The machine isn't going to see this before it's being tested on. It's not going to be trained. It's not going to be trained on this section. This is for testing to see how well it works. It has 30 rows, the tree variables, just like the training, and then the 30 labels. So it's going to see this, and then when it's being tested, and then it's going to have the labels to check if it was right or wrong, essentially. And now I'll go into more detail when I'm going into how the KNN model works, because it may still be a bit confusing. And yeah, so what else did I not explain? I didn't explain the random set. So random set is like, when we're splitting the day into training and testing, we're not taking um we're not taking a number that is we're not taking it sequentially. We're not taking the first 80, and say we were working with 100 for simplification. We're working with 100 data points. We're not taking the first 80 and leaving the next 20 for testing. It's randomized, and then the randomization state is just set to 42. It could be set to 6. It's just so that we're working off the same randomization, because there can be small differences in it's going to change every time. Your accuracy may change slightly every time, but we just want to be working off the same random state. That's why it's set to 42. You could equally use 600. It's just that we need to have the same random state. I think that's everything explained. And then what I've done here is I've just opened it so you can see. I've just said train data dot head, so you can see what we're looking at. The tree variables is what it'll be trained on, and it'll be trained on the labels associated to each So this, then that's Satosa, and the machine is being trained on what to see, and that's it. And then next up is how the KNN model works. Okay, this is the part we've been waiting for. The KNN model itself, how does it work? How does it classify? How will we use this to classify the flowers? So basically, the KNN model, in the most simplest form, it's just measuring the distance of data points. So I'll go here first and I'll say focus on the little circles. Focus on the little circles. It's similar to what we looked at up here, similar to what we looked at up here, and then we're bringing a data point. Now I'll go back again. I'll try not to make it too confusing. So just focus on circles. This is a scatter plot we're looking at, and the X is a data point that the model hasn't seen before, and we're trying to classify it using the model. All these data points here, they have been trained, they've been used to train the machine learning model. That's how the training works. And the machine learning model knows what category these belong to. So, say, for example, this is C1 represents Setosa, C2 represents Virginica, and C3 represents Versica. And then this, for this example, there's four. Obviously, we're working with tree, but just for the example, we'll just say this is like a rose. Now we brought a new data point, and then the y-axis, for example, say that's sepal width, and the x-axis is, uh, for example, sepal length, right? And then we have data, and they fall under this, like this data point falls under this sepal length and this sepal width, for example. And now we've brought in a new data point that falls here. So, well, thinking about anything, if you had to guess, because it works by essentially KNN, K nearest neighbors, if you had to guess, you would just say, well, even looking at the red, you'd say this belongs to C1, which I think I said was Setosa. Straight off the bat, you're saying that's likely a Setosa. And that is all the model is doing. It's classifying based on this. But to get into more detail, there's a hyperparameter where you can adjust the number of neighbors, and we'll go into more detail on that as well. So in this case, 1, 2, 3, 4, 5, 6 neighbors are used here. And now it will go by the distance between its nearest neighbor. So it's used 6, and the closest to X seem to be in C1. Now it's got one in C3 and one in C2, but it's gonna vote a voting structure because it's got four here, so it's more likely to be C1 than anything. So it will say when the machine goes to classify this, it's gonna classify it as C1 Setosa. I know there's different ways of measuring the distance. This is more detail that I think is required. And Minwaski is basically the between these two. Like it takes into consideration these two to measure the distance. But why it's defaulted, but why you might not always use it? That's a question I asked. Is because it's more complex to run, and it can be harder to explain, and harder to understand as well. So that's why you might want to use this, which is the numeric data. This for more like numeric data, and this is for more categorical data classification, which is what we're working with. But this is default, and you can tune this to get better results. Or you can use either one of these if you're not happy with how your machine learning model is working. It's something you can tune to improve your machine learning model. So I hope I've explained that well. Here's some data. Determine the K. Selection depends on your data and project requirements. So this is the number of Ks you want to use, the number of red lines. You don't want to use too little or too many. In this case, we're going to test between 1 and 9Ks to see which one gives the best predictions. It's a hyperparameter that you tune, calculate distance between the new input and all the training data. As with K, selection distance function also depends on the type of data. Sort the distance, determine the K nearest neighbors based on the minimum distance. This has the smallest distance to these, plus the Ks, gather the categories of those neighbors. So the neighbors here to this are in C1, and then determine the category based on majority vote determines that it's going to be C1. And that's how K nearest neighbor classifier is working. And now we'll go into how we're going to run it in Python. That was an explanation of how it works. I think that can be a separate video or a separate section. So I'll stop it there. Okay, here. So we've determined that the best neighbors is 3. We could possibly use 4. And now we see that then we're gonna fit we're setting our KNN, K neighbors classifier. This is just a shorthand of it. Instead of using, excuse me, using it's just easier to type out the code using just KNN. And we're setting the number of neighbors to 3. That's it. Then we're fitting the model, we're training using 3. We're trained using 3, then we're computing the accuracy, and we're computing the test accuracy score. And then let's display the test accuracy, and we're getting 96%. So when the machine sees data it wasn't trained on, new data points, it's 96% accurate. So what we've gained here is we're able to determine between the tree Setosa, versicolor, and virginica flowers with 96% accuracy. So when we feed this model those parameters, the petal length, petal width, no, sepal length, sepal width, and petal length, I believe, we're going to get 96% accuracy from this model. So it's very good at classifying which flower. So that's what we've created here. So that's the purpose. Now you can use it for more complex complex data, but this is what we're working with today. And then accuracy isn't always the best determination, because accuracy is how accurate it was. How many times do we get it wrong without looking at how many times the machine model made a mistake? So a confusion matrix will determine how many times a machine learning model gets something wrong. And this is important because, say, for example, we were classifying skin cancer, for example, and we if we keep classifying, yes, that's this cancer, yes, cancer, yes, cancer, yes, cancer, we go no cancer when it should have been yes, cancer. That can be very dangerous for obvious issues. So you need to also look at how often the machine learning model gets it wrong. So what I'm going to go into detail here is, so for we're going to look at precision. This is the confusion matrix. Confusion matrix goes so precision, recall, and F1 score. So precision is correctly predicted positive instances. I need this here because I always need to check it. I've been looking at this for years, but I always have to check it. So correctly predicted positive instances. So it said yes, cancer, incorrectly predicted positive. So this, for example, this would be so this is the true positive and false positive. So how often does the model, because if the model just keeps saying yes, cancer to stuff, and then when it's not even cancer as well, it's not that precise. So we're just trying to get how many times it keeps saying yes, and then how many times did it say yes when it was actually no, is your level of precision. So if there's a lot of times it's saying yes when it should have been no, your precision is going to be lower. And recall is kind of like the opposite of that. So how many times it's saying no when it should have been yes. Now, you're probably thinking, like with the cancer thing, with the cancer example, you want your, working with, say, classifying cancer on the skin, you're gonna want more precision than recall. You're gonna rather it to be more precise. You want to say, now that's not really good from an emotional standpoint, but just from, you really don't want to say no when it should have been yes, because that person's going to die. You will cause emotional distress if you said yes, and then there needs to be further tests, for example, when it should have been no, but that's better. So you want a more um, precise model than a recall model. But it's different for different aspects. Like if there's lower risk, you may, it depends on what you're working on. I can't think of an example now, but you need to look at both. So, and then the F1 score is the average between the two. So this model is very good at determining Sato's, as you can see here. It's perfect. And support is the amount of data points. So it's very good at support determining Satoza, but it's not that precise. So sometimes when it comes to versicolor, sometimes it's saying it's a versicolor when it's not. It's a false positive. It has some false positives in there, and then that will obviously reduce the average. If it was perfect like Satoza, it would be this. And then it's never saying it's not it's never giving false negatives, which is like I said earlier, it's instances where the model mispredicting positive class. Okay, let's go. Let's evaluate our model now. So in this sense, we're going to look at something. We're not just going to look at accuracy because accuracy doesn't take into account how many times the model got things wrong, which is important because what I use, which is a morbid example, say you're working with classifying skin cancer. So if the model gets it is 96% accurate, it looks great, but if it's getting a lot of things wrong, how it's getting it wrong is very important because if it's saying someone doesn't have cancer when someone does have skin cancer, that is life threatening. So you need to look at parameters from the confusion matrix, which is the precision, the precision and recall essentially are the main thing because the F1 score is the average and support is the number of data points used. So let's go into so precision has to do with it's when it says we'll use skin when it says when it looks at the model looks at classifying skin cancer, for example, it's gonna say positive. It says cancer, 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 and then sometimes it says it's cancer when it isn't cancer. So that's a false positive when it says that's cancer, but it's not cancer. So lower precision means you were saying that this model was saying something was cancer when it wasn't. And recall has to do with when it's saying it's cancer when it fails to determine its cancer and says it's not, it doesn't give the true positive, where it fails false negative where it says it's not cancer when it is. And now you can probably determine which one is better from in the in the cancer topic. When you're trying to classify skin cancer, you want it to be more precise. You know, you if you seen it was really precise, you'd be happier with that. Although it will cause a lot of distress if you're saying someone has cancer but they don't. But it will lead to death if the model's predicting no cancer when there is cancer. So in that topic, you want it to be more precise than want a greater precise than recall value. So, for example, when we're dealing with a less morbid situation, our topic of discussion, which is the Satoza, this model is perfect at classifying Satoza. Precise. It never says it's always true positive. Doesn't say it's Satoza when it isn't. It doesn't say it's not Satoza when it is Satoza. And then this is the average between two, which is expected to be perfect because this is perfect. Now, as versicolor, we can see it's gonna say it's versicolor, false positive when it's not sometimes. This is why we're still high, but this model is gonna do that. So it's something you look out for that if you see the model predicting vertically, you might be a bit okay. I'm pretty sure, but I don't know. Sometimes it does say it's vertical when it's not, but it never fails to determine versicolor. It always determines versicolor. It will say so. False negative is when it was versicolor, but it said it's not versicolor. So it's gonna catch versicolor, and Virginica is the opposite way around. So that's how this confusion matrix is working. I hope that's very clear. You can read the detail. Even sometimes when I'm working with the confusion matrix, I have to take a beat, think about it, then go back, and then it's fairly clear, and you can see the advantages of a precision using a precision matrix over just looking at the accuracy. All right. Like if this has been helpful, this process has been helpful for everybody, just like, subscribe. It wasn't easy to make. Thank you.